Hello everyone, I'm Tong from Tsinghua University, and today I will be presenting to you about combating packet collisions in LPWANs. This is a joint work with Professor Jiliang Wang and Professor Yunhao Liu. As we know, the unlicensed LP1 systems are suffering from severe packet collisions. LP1s are deployed in the star of stars network architecture, where thousands of nodes transmit to the same base station, while multiple nodes with the same physical configuration transmit concurrently. Their packets overlap at the receiver, leading to collisions. Such collisions cause frequent packet loss and also waste precious airtime and LP1 spectrum. Packets involved in the collision have to be retransmitted. This increases the energy consumption of the end nodes and also leads to a gap between the large-scale IoT vision and the LP1's practical capability. The collision problem should be carefully adjusted before applying LP1 for connecting millions of IoT devices. There are many researchers trying to resolve this collision problem, but all of these works have limitations. In particular, there are three main approaches to deal with the collision problem. The first is to deploy MAC and physical layer schemas to avoid collisions, such as RTS, DTS in Wi-Fi networks, or MIMO in Zigbee networks. This approach does not work because for low-cost LP1 devices, the hardware capability and power budget are both very limited, making it impossible to apply complex MAC or using multiple antennas on low-cost LP1 devices. The second approach is to apply successful interference cancellation to recover packets from signal collisions. The problem with the second approach is that it requires a high SNR for canceling interference and recover packets. Besides, traditional SIC algorithms have the problem of error accumulation, making it worse. The third approach is to exploit the hardware imperfection of low-cost LoRa devices to decompose overlapped chirp symbols. However, this approach does not scale well as a tiny frequency offset drifts over time and is difficult to extract. So, how can we deal with such packet collisions in LP1s? For resolving this problem, we propose NScale, an improved multi-packet reception protocol that can decode even in the presence of packet collisions. NScale is resilient to noise interference and can decode for extremely low SNR collisions. And it can also support large-scale IoT applications by decoding tens of concurrent transmissions. Finally, it is simple to deploy as it is fully implemented at the single antenna base station without any extra modification on end nodes. We implement a prototype of NScale with USRP software-defined radio and evaluate performance in a real deployed LoRaWAN system. Here is our idea underlying NScale. We try to leverage the packet time offsets to address this problem. Devices in LP1s transmit packets following a pure Aloha MAC protocol. It means packets can be transmitted anytime during the whole work duration. As a result, there may exist a random packet time offset between any two collided packets. The goal of NScale is to leverage this packet time offset for resolving collided LP1 packets. To understand how we can achieve this goal, we need to first understand the physical layer of LP1s. For the physical layer, it adopts the chirp spreading spectrum where signals are modulated into chirp symbols whose frequency change linearly over time. For encoding data bits, we shift the initial frequency of the chirp symbols. For example, to encode 1 bit, we use a base upchirp to represent 1 and use a shifted upchirp to represent 0. At the receiver, each encoded chirp is multiplied with a base downchirp, resulting in a single tone with the encoded initial frequency. Then, we apply FFT on the multiplication to transform each symbol to an FFT peak in the frequency domain. The frequency of these peaks represents the encoded data. To encode n bits with a single chirp, we can divide the chirp bandwidth into 2 to the power n different initial frequencies. And now, See multiple packets cleared at the receiver. In this example, packet A and packet B overlap with a packet time offset. And the receiver divides the signal into consecutive demodulation windows, each with a length same to the chirp. In the demodulation window, multiple chirp segments corresponding to different transmitters overlap with each other. The key to decode the packet collision is to correspond these segments to the correct transmitters. Our key observation is that in the time domain, chirps of different packets are distributed at different positions of the demodulation window. Therefore, we can recover packets from collisions by grouping symbols with the same in-window distributions. However, putting this idea into practice is still very challenging, as a settled time distribution for low SNR signal is difficult to extract. If we follow the traditional decoding procedure, signal in each demodulation window can be converted into energy peaks in the frequency domain. Receiver can decode the low SNR signal from those frequency peaks. Because by converting signal into the frequency domain, the energy of useful signal add up constructively, while noise add up incoherently. However, after the FFT, the time information of each chirp is completely lost, making it impossible to identify which peak corresponds to which packet from the in-window time distributions. Now, let's see how NScale addresses this problem. The goal of NScale is to convert chirps into energy peaks, as well as reserving the in-window distribution information. To achieve this, NScale adopts a non-stationary scaled down chirp for signal demodulation. A non-stationary scaled down chirp is generated by scaling the amplitude of a down chirp differently at different positions. At this point, chirps at different parts of the demodulation window contribute differently to the height of FFT peaks. So by analyzing the height of those frequency domain peaks, we can recover the in-window distribution of their corresponding time domain chirps. Particularly, NScale mainly involves 3 steps. First, for signals in each demodulation window, we multiply it with a base down chirp and perform FFT to get energy peaks in the frequency domain. Then, we also multiply the received signal with a non-stationary scaled down chirp by varying the amplitude over time, and we transform the multiplication to energy peaks in the frequency domain also by FFT. And finally, we pair the energy peaks from the above 2 steps according to the peak indexes and calculate peak scaling factors as a height ratio of each pair of peaks. In this example, the peak scaling factors corresponding to the 3 chirp segments are alpha 1, alpha 2, and alpha 3, depending on which part of the non-stationary scaled down chirp is multiplied with the chirp segment. Now, we can say the non-stationary scaling reserves the time information of collider chirps by translating their in-window time distribution to peak scaling factors. This is important because it allows us to separate collisions, since peaks with the same scaling factor are of the same packet. Also, as peaks in the frequency domain are robust to noise interference, the benefit of LPWAN for decoding low SNR signal is reserved. Now I will introduce how to design the non-stationary scaling. The first rule for non-stationary scaling is being monotonous. For a non-monotonous scaling function, symbols with different in-window time distributions may result in the same peak scaling factors, leading to ambiguity. Let's use an example to make it more clear. Say we have a non-monotonous scaling down chirp for resolving a 2-packet collision. Essentially, the peak scaling factor is the average of the scaling function during the segment duration. For the chirp segment 1 and the chirp segment 2 with different symbol lengths, they multiplied with different position of the scaled down chirp. But the peak scaling factor corresponding to these 2 chirp segments can be the same as each other because the scaling function goes non-monotonous during the chirp duration. This leads to an ambiguity for distinguish these 2 collider packets. The scaling function should also be linear. A linear scaling function can maximize the average distance between any two different peak scaling factors, leading to a better performance for separating collided packets. And also, a linear scaling function is easy to achieve with commercial hardware. More details about the scaling function analysis can be found in the paper. Okay, to put everything together, in order for us to decode packets from LPWAN collisions, we will first demodulate the collision signal with both a base downchirp and a non-stationary scaled downchirp. And we calculate the peak scaling factors for all the detected FFT peaks. Then we group those FFT peaks into multiple clusters according to the peak scaling factors, each group corresponding to a collided packet. And finally, we can decode these recovered packets after resolving the packet time offsets for each chirp symbols. All right, so now let's see how NScale works in practice. We implement NScale with USRP software-defined radio, and our base station uses a single antenna with a commercial low-noise amplifier. By default, the bandwidth of the base station is 125 kHz, and it operates at 470 MHz bands. Finally, because of the delays in software radios, we use MATLAB for processing the received physical samples offline. We evaluate the performance of NScale in two different scenarios. The first is an indoor testbed with 40 LPWAN end nodes. Each end node consists of a Symantec real chip and placed at a fixed position of a shelf. All the end nodes are connected to a backbone network through the Raspberry Pis, and that information from them can be efficiently collected. We also build an outdoor LPWAN system. Each node is connected to a temperature and humidity sensor and can collect and transmit sensor data to the base station periodically. We deploy those nodes at over 30 different locations of the campus, such as buildings, roadsides, and parking lots. Let's first look at the throughput performance regarding to different levels of SNRs. We use the testbed nodes to generate packet collisions, and we configure one node to send beacons every 3 seconds. Upon receiving a beacon, the other two nodes each replace with a LoRa packet to generate collisions. The original LoRa one cannot resolve collisions, so its throughput is always close to 0. MLoRa uses the SIC-based approach for decoding packet collisions, and as the SNR decreases, the throughput of MLoRa also decreases rapidly. This is because it utilizes the high SNR for accurately constructing and canceling interference. Choir uses the hardware offsets to distinguish collided symbols, but in practice, the frequency offsets for low-cost LoRa nodes drift over time, and this leads to a symbol classifying error. NScale outperforms the R3 methods in this evaluation. It works well even on the extremely low SNR. The one packet is collided under the SNR of -10 dB. The network throughput of NScale is about 3.3 times of choir. Next, we explore the impact of packet time offsets. We still use the indoor testbed nodes, and we configure one additional processing delay for each transmitter to generate different packet time offsets. We perform the evaluation on the 3 different SNR levels. And one packet is cleared with a small inter-symbol time offset. The SER of NScale is significantly high. This is because a small offset leads to a small difference between in-window distributions, which further make it difficult to distinguish collided packets. But for most of the packet misaligned situations, NScale can decode most of the symbols on all the 3 SNRs. Now, let's focus on the scalability performance for decoding packet collisions with different number of concurrent transmissions. The network throughput of both choir and NScale increase as there are more concurrent transmissions. This is due to the benefit of multi-packet reception from collision resolution. Meanwhile, The network throughput of Qi is much lower than that of NScale, especially for the large concurrent situations. Finally, we evaluate the performance of NScale in a real deployed LoRa network. The performance of NScale is much better than that of original LoRaWAN due to the NScale can decode from collisions. For the LoRaWAN receiver, once the network size is small, the increase of concurrent nodes improves the channel utilization. However, once the network scales, collisions occur frequently, which significantly degrades the performance of LoRaWAN receiver. When 30 sensor nodes are operating simultaneously, the network throughput of NScale is about 27 times than that of original LoRaWAN. To summarize, in this paper, we present NScale for enabling LPWAN receivers to decode in presence of packet collisions. NScale is robust to noise interference and also perform well for hardware offsets. We implemented and evaluated the NScale base station with USRP and in a real deployed LPWAN system. The results show that NScale can convert non-decodable collisions to operational links, and it improves the throughput, latency, and battery life for the LPWAN nodes. Okay, that's all. Thank you for listening.